Of moment of inertia using bifilar suspension. Let me I know, but today is Saturday. I have my own class. Look at the time, you see we don't have time. So if I choose that part, it means you are not doing physics 107 today. So on Monday we'll go back to physics 101. Determination of moments of inertia using bifilar suspension. I think
55.
on the old manual 55. So the new student just then check the table of contents. See which one talks about. Please, before you go for break, those of you that have not gotten biology past question, it's inside the 3 in 1. Come and meet me. That is inside the 5 in 1, it's the 3 in 1. This past question contains all your lecture courses, so you come and get it before you go. So that is the spelling of bifilar suspension. Write for me as a subtopic. New manual, I'm not sure of the page. The first question is 5 in 1, chemistry, physics, maths, GST. About 3,000. No, you can't bargain. Whatever price we are telling you, simply means that's the right price. Huh? Show her. Because make an eye son and some people do not get it back. You forget it. Forget where I love one does it. It's at that day you gave. You forgot this one. So anyone that wants to speak at so right for me as a subtopic, moment of inertia. Let's define what we are treating. Then I will explain. Then we'll talk about this practical. So we said a moment of inertia is the measure. We say a moment of inertia is the measure we say that moment of inertia is the measure of resistance. This is the way physicists defined it. But I will give you the correct explanation because this definition, I don't like it. We say it's the measure of the resistance of a body along an axis. It is the measure of resistance of a body, along an axis of rotation. The rotation is me that put it, or that rotation is me that put it. It's simply the measure of resistance of a body along an axis. So put of rotation. You only talk of moment of inertia when a body is rotating. That's the first thing you need to note. If a body is not rotating, what you just talk about is mass. Can you hear me? If a body is not rotating, you just talk about the mass of that body. But once a body has to rotate, what you are talking about is what we call inertia. Can you hear me? So I will explain what that means. I said it is the measure of resistance of a body along an axis of rotation. So whenever I talk about force, see, whenever I talk about force, normally force that happens normal, we know that it's MA, Shebi? Is it not? But when I want to talk about force at an angle, that is something that has to make it rotate. I am talking about torque. And as we progress, I will tell you that torque is equal to inertia. And I will still teach you that as we progress when we enter rigid body. So you you need to know that mass is when you are treating of a body either at an axis y or x. But once you are not talking about that body going through an angle that is rotating through the two surfaces, that is x and y at the same time, what you are not talking about is inertia. So physicists defined it that you think of inertia as mass distribution and how hard it is for a body to rotate. That's how physicists see it. So see what I mean. Inertia is simply given by mr squared. You've heard of this, Shemi? You've come across this before? No. Yes. Okay. Please, this thing that you see here is when that particular surface is well distributed. When we enter rigid bodies, you will see that we have different inertias. We have inertia for sphere, for cylinder, for disc. You will start seeing us deriving it. We will start using certain principles to derive it. But for the meantime, the general rule is that inertia talks about mass. And because the body is rotating at an axis of y-axis is the one arrow, this side is another arrow, that is arrow square. Remember that when we are treating circle, we said that the motion of circle is simply when I'm dealing with vertical and horizontal shaping, and what we treat here is just arrow. Is it not from here to here? So if I know it, when it has to do with inertia, we are considering this as one part, this as another part. That is the arrow here, the arrow from this end to this end, from this end to this end. So what I'm trying to make you get is what inertia is, but that is not what this practical is all about. It's not only about inertia. So once you've gotten this principle, that whenever you are talking about mass, it has to do with maybe just this way or just this way. But whenever you are talking about mass that is rotating, you don't call it mass. You consider it in terms of inertia. You get the point now? Yes. What? I didn't hear you. What does the R square means radius now? Radius times 2. Radius times 2. Radius on this axis and on this axis. That is why we say that when considering inertia, you are actually considering it as mass distribution. It's no longer when you are saying that radius on this side is the same thing with this side. You are considering it that the mass distribution on the y-axis, mass distribution on the x-axis. So when we enter rigid body proper, I will still throw more light on it. It will become clearer. But please, once you hear a body is rotating, what you consider as mass there is inertia. Alright, now let's go to this practical, please. Bifilar, this thing is the same thing, it's just that textbooks spoke the same language. Normally, I will not use this bifilar, I will just say by two-thread method. This bi here simply means two. This filler simply means thread. In secondary school, you did this practical. Do you still remember? You did not do it. Okay, you did not do YL. You just entered here. It's well. It's well. So please, by filler, this English simply means by getting moment of inertia using two-thread suspension. That is just what he's talking about. And please, provided, let's say I did not take part in the practical, I'll still teach you how to do the practical. Do you remember that from simple pendulum, you have period to be 2 pi root L over G, shaping? Yes. But whenever it has to do with bifilar suspension or by two-thread, or you are talking about moment of inertia, please, the formula for me is just come to this particular formula. We know that it's very easy. Put I anywhere. You know that multiplication is distributive, commutative, associative. So put I anywhere at all. Then work is mg shaping and d, right? Shaping. So the idea I want you to think of is once you've written this, come and bring md, but now the d is carrying square. So please, for equation for moment of inertia, it is simply the same thing as saying 2 pi IL all over f d squared. Whichever one you want to use, because mg means force shaping, Which means that this is the same thing as saying 2 pi root IL all over work D. Are you aware? Because work is simply first times displacement, Shebi. Then you have another. So whichever one you come across, it is still the same thing. But the main thing is that we normally say that determination of moment of inertia by Bifilar suspension is similar. It's similar to simple pendulum, but there's a difference that we'll point out as we start practicing what the practical looks like. So whichever one you think of, once you have the equation of a simple pendulum, the top, because you're talking about moment of inertia, you have I, the down, you just add M this called, you say you add work done and displacement extra. So whichever one you are using is the same thing. So with that said, let's now analyze what this practical is. And please, do you remember? Can I clean?
Yes.
How can I be teaching something like this? You are carrying bag. Something as important as this, you are carrying bag. Onega, I hope you are coming back. Thank you. Very important. Physics 107, you will write the exam. I see. Before I start the practical part, please, do you know that this means that this is directly proportional to, I will ignore this 2 by, because this is the same as K. Hope you know. Shall we know that this is K? Because it's constant. So it means that T is directly proportional to inertia and it's directly proportional to length. I'll still tell you what length I'm talking about. And it also means that T is inversely to mass, and to displacement, that is distance squared, and it's also inversely proportional to gravity. Hope you remember. That is what this formula means. And you know that we have square roots here, but no need putting it. So it means that as we are doing time, if we are finding time, if the distance apart is big, the time will be small. If the time is big, the distance apart will be small. Okay, we've noted this equation. Let's now try to analyze what the practical is all about. Because I know you did it in secondary school. Okay, if you did not do it, the first thing to note is that I am provided with a retort stand. We know what retort stand is, actually. I am provided with a retort stand. Okay? 2 retort stands for that matter. So I think in order to draw this well, if I have done my 2 retort stands, if I have my 2 retort stands, I will have the opportunity of attaching ropes to that retort stand. Please, this is the leg of the retort stand, one retort stand, the leg of another retort stand. Now I will attach rope from that retort stand. Attach rope. So please, you know what retort stand looks like in the practical lab. So I put this rope. This rope runs on its own down. It doesn't stop here. But this is to show you that it passes and runs down. Now, the measurement for the rope depends on what the lecturer asks you to use as the measurement, the distance of the rope. So let's say, generally, in my practicals, they normally tell you that you should make the rope to have distance from this end to this end to be 70. So please, I don't want to put this retort stand here, not to confuse you. You have your rope attached to the retort stand, it's running down. Your retort stand this way, retort stand this way, you put rope on it, it comes down. Put rope on it, it comes down. You measure with your meter rope 70. So this 70 that you measure, this 70 that I have here is the centimeter. This is the elbow that I'm talking about here. In some textbook, you see it as edge. Now, if I've gotten this elbow, notice that this is the first retort stand. Shidi? That is the rope from the first retort stand. This is the rope from the second retort stand. The distance from this end to this end is the D that I have here. That D that I see there, that is the distance. That is the D. Now, if I know that, in between, I'll still post a video doing this practical, like this practical well. I'll post a video of myself doing it on that my page. I'll still post it on the paid group. So you put a meter rule. Yes, the rule is that I'm using, can I claim? I'm provided, inside the practical lab, I'm provided, I have access to A, 2 retort stands, B, I can even be given knife edge, maybe to balance the ruler first and find the center of gravity. But I don't have to find center of gravity since the practical did not say we should use mass. It's distance we are using. So I'll teach you the 2 ways of doing this practical. When they give me mass, and when they say I should use distance to do the practical. So B, I am provided with rope or string. Rope or string. Something I attach to that, rope or wire or string. Now, C, meter rule. So I have the meter rule that I will pass to run through this particular wire. Because once I attach this, if I measure that 70, the extra of the rope that is remaining, I use it to tie the meter rule. So the meter rule is being placed horizontally. You get the point? It's placed horizontally. So this is my meter rule. I am seeing the path, but on the inside, as it passes through this, is more of having this nature inside. So inside that rope. So I'm tying it to it. Now, so I now have this. So I have my rope attached to it on that meter rope. So what I will now check is the distance from this end to this end. The distance from this end to this end, I get it. That is the distance I am using. That is the first distance. So let's say on this part of the meter rope, from this end to this end, I have like 15 cm. Or let's say, sorry, let's say something even. Let's say I have 10. And on this end, I have 90. Okay, if you pay attention, you will hear me, you will understand. I said, I have put this meter rule. You know that the meter rule we use is the long meter rule of 100 centimeters. Yes. Now, from the 0 mark of the meter rule, any point at all, me, I'm teaching you based on my X standard and advanced lab standard. That is. But if your lecturer decides that the measurement where you place your rope is maybe 4 cm, 10 cm, however it is, whatever measurement, that's where you're placing the first rope. Then the other end you place, but here I'm using my rope is placed first on the 10 centimeter mark. The second one, I'm attaching it, tying it to be 90. So at the end of the day, you will see that you are now having your meter rope being carried by these 2 strings. It will hang because this is tying it, strong rope, tying it, not like it's strong, like too rigid. The same thing here, tying it. Now it is now carrying it. So if you now measure the distance from here to here, it's the same thing as saying 90 minus 10. Is it not true? So that means that it's around 80, should be? Yes. 80. Yes, so let's say the first distance I have is 80. That is my D1. I can do this practical. When I rotate, I will do it twice. And when I want to do the second experiment, since they did not say I should use mass, the second way of doing this practical is, as you determine meter rule, the center is always 50 or 50.2 thereabouts. Assuming it's mass they gave us, but this particular one did not make provision for mass. Assuming it's mass they say we should use to do this practical, I will just come to the center of gravity, place that mass, the kg, maybe 30 grams or 40 kg, whatever, I'll place it on top here. After putting this on, I'll come and put it here. That means when I'm using mass, I don't have to adjust this rope to be changing the measurements. what I'll be using is, if I finish the first one after I rotate, I'll remove this mass. Put another one, use masking tape, glue it. Do the rotation again. Remove it. Put another mass, glue it, rotate it. And how you rotate this is different from simple pendulum. A simple pendulum, you do swinging, Shibi? But in this one, what you are doing is you are holding this meter rule this way, holding this way, so that you are dragging it, you are making angular displacement. It's more like I have this. I'm not pushing it to come and do like this, or pushing it to come and do like this. What I'm doing is, as I have it like this, I slightly push this part and push this part and I leave it, so that it is now moving this way. You get it now? Yes. So it is not moving this way. It is not moving this way. Rather, it is more like turning. Yes, it's trying to turn. Angular displacement. So I push it in a way that when I post the video, you see it more. Because it's a shame that we are doing this without. This is one practical that requires us doing the practical. So you push it in a way that as it's moving, it is trying to turn. But because it is having equal measurements, or should I say, because the weights, and you did not really push it too much, it will be moving like this. This one come, this one go, this one come, this one go. If you do it too much, it's part of the procedure. If you do this thing too much, what you end up doing is, you might end up scattering the rope, or the rope will leave the rector stand, or this thing will end up doing one kind, like haphazardly, until it gets its balance. So part of the procedure is that when you are giving it that angular displacement, you are doing it gently. That's part of the procedure. You do that gently. The displacement should be gentle. And the displacement should be at an angle. Notice that this thing that I'm doing now, when I push this thing like this, it's vertical. Or maybe I push it like this, it's horizontal. That is more like I'm saying, I'm going this way, backwards, or I'm going left and right. It's not at an angle, it's just 90. But when I do this thing this way, I am trying to turn this at 360, but I can't. So it's more like maintaining an angle, not 360, but it's going at an angle, trying to revolve. So that is one of the procedures. So, one, the displacement should be at an angle. So it doesn't just move back and forth, or left and right. So displacement should be at an angle. At an angle. Let's be fast. At an angle. The displacement should be gentle. The displacement should be gentle. The displacement should be gentle. The meter rule must be clamped. The meter rule must be clamped horizontally. If this meter rule, you decide you want to invent, you carry your own place how you want. Or you maybe, you come and do the measurement of here to be 70. This one is 60. It's looking like chamfer. You are wrong. So the meter rule must be clamped horizontally. So number 4, these are parts of procedures. So the procedures. So the ropes, or you say strings, or you say wire, must be parallel. By parallel, it means that there should also be having parallel / having equal lengths to the meter rule. To the meter rule. Sometimes they call meter rule. Doing this practical, you see them call meter rule bang. Bang. It's the same thing. So these are procedures. As we progress, more of it will come to my head. We'll still write it out because each stage of practical tells you the procedures to take. So as I've noted this now, since we said that we are not using mass, they did not make provision for mass in our table. That means that what we are going to be making use of is simply just the way it is clamped now. I will come here, hold it like this. I leave it, it will move. As it's moving, I on my stopwatch. I'll be going to do 1, 2, 3, 4, up to 20 oscillations, because that's what the question is asking us for. 20. Assuming the practical asked you, maybe in exam, pay attention. It's not maybe the same thing you did in practical. You go inside the exam hall, you don't pay attention to what they gave you. You go and run and use what you did in practical. So assuming they say it's 10, as I rotate it, move 1, 2, 3, 4, 5, up to 10 oscillations. I stop that stopwatch. I check the time. I do it again, I check the time. This is what I will do for the different masses. Now, how do I now get different masses? Notice that this one, from this end to this end, gave me 70, Shebi. If 80, sorry, no, 80 is the rope that is actually 70, Shebi. So, if I want to do the second time for the second distance, this is the first distance. So, depending on, they did not give you distance. So, if I want to do the second one, I can choose to say, let me open this thing, like close it more. So, let's say I now carry this rope now. Instead of 90, I'm now having it at 80 and 10. Are you getting the point now? Or maybe 80 and let's say 20. It's up to you, depending on what the examiner is asking for. So once you've placed it, once you've changed the position, you do the same thing. As it's moving, you on your stopwatch, time it. You don't have to do, immediately you do it, you on stopwatch. No. What you know is that as you've done that, it's now moving. You on your stopwatch, count 20 oscillations there, you stop. So what you are checking is still, okay. That's what I'm saying, and I'm saying that your lecturer, when you're doing this practical, can come and say, use the distances of your choice, or he can come, outline the distances and tell you, the first one maybe space of 4 cm, or space of 10 cm, or space of 80 cm. It's up to your lecturer to determine that. But what you now know is that if you are doing this on your own, even without doing this practical, your mind should tell you that the lesser the distance, the more time. Because if you check that equation, and the more the distance, the lesser the time. So even if you have to do this thing without doing the practical, you must understand that rule. That if you have bigger times, bigger distance, and you are having bigger time, automatically you are failing the practical already. So it should still tally with the equation of the practical. So what we are saying here is, in this case, we are trying to take it that we are being given, let's say we are given distance of 80, 70, 60, 50, and 40. Let's say this is the distance we are given. So let's say this is the distance we are given. In this case, it simply means that what I need is simply, as I've done this one to be 10 and 20, Shebi, I can choose to now say, let's say I, as somebody that knows how to think, so that everything maintain balance, I can choose to reduce this one by 5, reduce this side by 5. You get the point now? At the end of the day, you've removed that 10 to get 70. You stay swing, not swing, you stay displaced at an angle. Because remember what I told you moment of inertia is. It is simply you talking about mass whenever a body is engaged in rotation. The minute a body is engaged in rotation, you are now talking about inertia. So what you are checking is the resistance of this metal rule as you try to rotate it. What is its resistance? How free is it at this distance or when it's carrying a mass? So that is why I told you that that torque we treated as that time we treated torque. As we progress into rigid bodies, you will now start to see that we'll be using slide to remove anything that involves FR to now come and put inertia here as we progress. Because that is the right principle, the right idea of moment of inertia. It takes over mass once mass or a body is in rotation. So if I've noted this, notice that we are not giving time here, shall we? Because we are not doing this practical in real time. Is it not true? But we can actually get our time. Provided we know the equation. Do you know? Okay. So please, you've noted this. More of the procedures will come as we progress. But please, you need to know that there are things that we started with. There are things we started with on our own. The length of this rope, we know it. Is it not true? Yes. We know that this is L equals to 70 cm. Let's say your lecturer decides to give you otherwise, but the length of that rope must be given. It is a must. They don't tell you to go and measure that one or maybe do practical on that one. It must be given. G as well. We know that G is 9.8. In fact, at this stage of us being serious, I want us to start using G as 9.8 meter. And we know that this is the sentence as 980 centimeters per second ahead. So, if I've noted this, we also know that this meter rule that we have must have a mass. Are you aware? Yes. Yes. Meter rule. Every meter rule has its mass. So it ranges from 80 kilogram thereabouts. So we definitely will have the mass of the meter rule. I want to be sure of this mass, the exact value, around 80 something. Somebody please check for me the mass, the standard mass of the meter rule. Please check. Just 86. You see what you have there? Where did you see it? Let me be sure. I just know it's in the range of 8 something. I think it's 80. Let's be sure of what we are working with. Okay. When did you copy this one? Okay. But this one is in meter now. This one is length. Is it not? It's 6 centimeters that you have there. Like I'm talking about the mass. 100 grams. Is it one? 0.12 kg. That is around what in gram? Let's just use 100 grams. 120. Well, let's go for 120. It's making me like it should be 180 grams. Well, let's use it like that. Okay, you're saying 100. I think, please be sure, verify. Let it not be that they are using the measurement. I know that meter rule is 100 centimeters. Let it not be that they are using the meter for the gram. My mind is just telling me to use 8. My mind is telling me to use 8 because in so many of the practicals, so please, if it's not 100 on your own, no problem. But we use 80 for the sake of old-time knowledge and experience. So 80 grams for the mass. So whatever your lecturer asks you to use, no problem. But the book itself, what mass did they give? That page, the old manual, what did they give us the mass of meter rule? Check. What did they give us as the mass of the meter rule? They not give anything. Okay, so please let's use 80. Let's use 80. Okay, then notice. So we have length in centimeter and this is in gram. So let's say we want to convert each one to each unit. 70 cm to this SI unit. 70 cm to meter is what? 0.7. Hope you know how to get it. Okay. Then this one, Uncle. 2 kg. 0.08. You divide it by 1,000. 0.008. 0.08. Okay. In kg, Shemi? We've done conversion before. We don't want to do it again. Okay. So now see. Let's check something. But the problem we'll have using this formula now This is T equals to root IL over. Shebi, the problem we have with this is that we don't actually know this I. Sure, you know. Yes, we don't know it. Because for us to determine the time, that is the period. Remember there's another one, that is, this is time for one oscillation, sure you know. Then we have the one that is T for 20 or maybe 10, which is equals to time for one oscillation times the number of oscillation, which is N. So in this case where it's 20, it's now 21 then times 20. Sure you still remember these two formulas. This one is time for 20 oscillations. This one is time for one oscillation. This is the one you call period. It is equals to this formula for this practical. But for 20 oscillation is simply time for one oscillation times the number of oscillations. So a situation whereby I don't know these two, because I could have said let me use this one to find this, make this one solid or formula. That means that period is also T20 divided by number of oscillations. That is time for 20 oscillations divided by number. But since I don't have these two, it simply means I need to do this practical. Sure you see it? Because moment of inertia is part of what you will determine. It's something you must determine. And they did not provide you with period. They did not provide you with period. Hope you can hear me. It's not like simple pendulum where we know gravity already. Then please, do you remember that this thing is supposed to carry K? And our K is what? 2y. Thank you. So for that reason, we will assume values for this. Or instead of assuming values, we can say moment of inertia for this particular practical is always around 3.0 thereabouts. Did they give you moment of inertia in that book? They didn't give us, we have to determine it. So please, that means what we are taking is time. We will just take time. We'll just use what we know now to take time. So we simply note that for the fact that this one is smaller, the time should be bigger. You understand? So that means I should be having, let's say, 34, 28, 24, 20, 16 in seconds. Hope you understand what I'm doing here. No. I'm using the principle. You may take a no, may see no. See, this is D now. D is inversely proportional to D, Shebi. That means that the bigger the distance. Shebi, why the smaller the distance, the bigger the time. That is what I just did there. So I assumed 34. I assumed that, and it's not just that I assumed. I used close values that you use when it's YN, when you do this practical. It's always ranging, if you have, should I say, that range of, let's say, 44 meter gap or 44 cm gap. It's always ranging within 434 thereabouts coming down. So I just assume in regards to, that is YN scheme of work. So please, what I want you to do is when you get home as you are studying this, or when you start getting these practicals, because you say you've not done it, you just now know that whatever value you are getting at that point, your own is you're taking the knowledge we have here to graft what you are doing there. Because what it simply means is that this is not part of the practicals you say, even if you did not do the practical, you can do this, you can do that. Because you have two unknowns in this practical. Anytime you have two unknowns, you can't assume again. You've been totally limited. So if I know that I'll be giving these seconds, is at this junction I can now start saying, okay, and you know that this time here is actually for 20 oscillations, Shebi? Yes. Shebi, you remember? Yes. Because each distance you have here, each distance you have here, each distance you have here is the distance you use to do 20 oscillations. Shebi, you still remember? So when you are actually doing your practical most of the time, it's not period you are finding. What you are finding is the time for a particular oscillation, which is this smaller thing that I put here. So let me just put it. So I will now, okay, we've noted how to do this practical, which I said I will still post the video. Notice that anyone I tell you I must post the video, I always post. Even the quadratic equation we talked about, I've posted it. Take your time to watch it. to see how and the reason why we draw the middle term. Today I'll post a practical video of myself in the lab doing this thing so that you will use it to study, see how angular displacement is coming. Now please, with that said, I want to see, like, give me your table. Let me use your table to graph.
We have not done anything.
Okay, new man that does not have it. It's not possible. Okay, it's only your other ass table.
Okay, is it table?
This is table now. Not table.
I thought it's validation.
No, they won't give you plates.
How are you going to draw your
Story. Us is so we're not doing. You're playing now. You think we are playing?
The man, Dr. Chimane, us is that those are the practical that has already a few tables that we should go and do this. We bring out one from that one.
Come again. Like you say.
Us here, that those alternatives to practical that we think we should go and do. That we have to learn it very well. But from that one of those alternatives to practical, and you bring out questions. Like, you know, questions.
Okay, what you're saying in summary is that he's not going to teach you people any of the practical, but you people should go and study.
Study those alternatives to the practical. Those are the giving us tables. Like, they did it, give us tables.
Okay, that means you shouldn't do any of the practicals outside the alternative to practical. That is. The thing when I don't know what I do. So no, see, what's the takeaway? Forget what he said. What's the takeaway?
Let's be doing those ones
those ones that you bring out in exam. Are you not aware that this one I'm teaching you? Have you not seen past question of 107 last year? Okay, you've not seen 107 past question last year. Both cantilever, Bifilar, that is thread, was there last year. So I'm teaching you in line with what we did last year. So, but if you say that Dr. Chim has said, the takeaway. Okay, please, the takeaway is that you want us to focus on alternative to practical. That's your takeaway. So please, what you will do for me is, those alternative to practical. It's not about who are you. She's saying what lecturer said. So what you do for me is snap those alternative to practicals. Or should I say the numbers? Write it out to me so that we use it as the word. Okay, see, please, if you don't have table on your own, what you can do for me is find a note, jot down all these things. Have you not noticed that we are now using Saturdays for just practicals? So we have a lot of Saturdays. If you say it's alternative to practicals you want, we will do it. But please, find notes, draft out the table. Why those of you that have the old one, let me see your table so that I can use it to do what we are doing. So please, fear not. If it's alternative to practical that Dr. Chima wants to use this year, that means we will try and do all the alternative to practical. Okay, so we're trying to fill the table and answer the questions. The only thing we will not do is to plot graph because I've taught you how to plot graph. So we'll answer all the questions there quickly. No, don't argue again. Hello, no arguments. What I know is that once we finish this one, I know we've not done simple pendulum. I will post the video because it's too simple. Compound pendulum, too simple. So once we finish this one, we do cantilever. We can now start your alternative to practical. Let me be sure I've covered the ones they did last year. We'll now start alternative to practicals. So fear not. We have enough time for all those. So please, you've written this down, Shemi. Because you've been calling it for me. You've been calling all these things for me, those distances. So please, we are using our need to be 40, Shemi. 50, and you've noted how to space this distance. We are using 60, 70, and 80. So if I look at this is serial number 1, 2. That is the number of observations. 3, 4, 5. Oh yeah, please look for me. 1/4 is what? Participate. Eze, where are you looking at? Febo Shemi? You are looking outside. Don't know. 0.025. So, where? 0.02. 0.02. That means this should be 0.03, Shemi. I want to believe we all understand. We all agreed to use 40, 50, 60, 70, and 80, Shemi. And we know our reason, right? But when you are doing practical, they happen to give you a different design. So that means you're not putting this inside your graph manual. Shemi, you know. Yes. So it's for them. So 1/6, you know. 0.016. Okay, 1/70. 0.0. 1/80. Okay, now time for 20 oscillations. Do you remember that our principle? The lesser the distance, the more the yes. And how do we get it? By knowing that T varies directly with IL, inertia and length of that road, and then inversely with mass G. This thing can mean many things in case they come and put it to you in any way. You remember it. So time for 20 oscillations will simply be what?
24.
Shemi?
28. 24. 20.
How we got it is that we varied it by saying the bigger the distance, the lesser the time. We now started with 34. If you go and check any wire practical, you will see that even if they maybe have maybe 34.02 or whatever, it will still fall within that range of space of 5, 4 thereabouts. So you can go and check for any wire practical on this. So let's say this is 02, 03, 0.02, 0.04, 0.01. So I'm using 2 decimal places. So this is, let's say this is 0000. Well, ask me.
And I think you say that they are divided by 4 or maybe by 4, something like that. Why is it 34?
It's moving now. Nice. The lesser distance there is 40. Okay. What I noticed, what she's trying to say is that this one is having space of 6, Shemi? Yes. But if you notice, 6 is not far from 4 now. Yes. So I just made that assumption. So if you want to use your own 32, no problem. But please, just get the points. Get the points. Assuming they gave us values for this now, it will be easier. Okay? Well, let's say I use 32. So that everybody will be happy. Oh yeah, now see. The period here, Shebi, you know I don't know this Shebi? Yes. But Shebi, you know that if I want to get period, I can as well say T is equals to, if you remember, time for 20 oscillation is equals to time for 1 oscillation times number of oscillation. Which means that this can be the same thing as saying T20 all over number of oscillation, which is 20, Shebi? Yes. So this means that T can also be, in this one, I will have 32.02 all over 20. 1.601. 601, which is 1.60. So I can also have 28.03. 1.40. So do for me 24.02. 1.20. I do for me 20. 1.00. I do for me 16.
0.81.
0.80. 80. Okay. So I've gotten the table, I've filled it. The main thing is that you have the idea, you know how to do the practical. Then when you see the video, you watch it again for thorough understanding. So that when you enter the lab and you're doing this practical, there is something we call assimilation. It's not about maybe you see something, you read it, you say you've read it. It's about how much time you took to think about it from different angles. It now settled inside you. You've learned it from different ways, different phases. So that is what I want you to do when I post the video. So you watch that practical and then read your own meaning into it differently. Now, if I've gotten this, I can go back to get the moment of inertia. I can go back to the question. I can go back to the question I said, because that's the first question I'm seeing there, Shemi.
Yeah.
They said, what is moment of inertia? Shemi? Okay, plot a graph of what and what?
D against 1 over D.
Okay, this one against this one. Okay, that means a graph of period. A graph of period T against 1 over D. Like this. That means that at the end of the day, do you know what it means? You are having T divided by 1 over D, Shemi? Because that's what slope is now. Yeah. Slope is the y-axis. Whenever you hear against, that part that is against is on the y. This one is on the x, Shemi? Yeah. That means that this is essentially saying T times D over 1. That means your slope is simply TD. Yeah. So you will now do the graph plot. And do you know what this thing means as well? Now see, Shemi, you know we can come here and actually, whenever they tell us to plot slope, we come and do, how do we get this T to be divided by D from this thing? Shall you still remember that method? Yes. Let's try it. This is I, L, not 1 over. This is I, this one is 1 over D, that this one. So let's analyze this, our equation. So I have T directly proportional. I want to represent 2 pi with K equals to K root L I or IL over mgd squared. Why I showed you the other ways of doing this is in case you see a question in the exam that writes it the other way. Okay, we have enough space today. Not really. To make we do square both sides. So if I square both sides, I'll have T squared. K squared, Shemi? Then Shemi, because this thing will cancel this. Yes. So I now have T squared times mgd squared. That is anything crossing equality sign. Yes. Is equals to K squared IL, right? Yes. Okay. Which one is my value? So if I remember what we are trying to do is to get the slope. Because to get I, if I want to get I, it's easy. I think I will get I then continue with the slope. That is to get moment of inertia, the equation I will use. I can say divide both sides by K square L. Shemi? Let's just get this one and then go back, continue with what we are doing. So this will cancel this will cancel this. So I now have the moment of inertia is simply T square mgd square all over. Do you remember that where K is equals to 2 pi, right? Yes. That means it will be 4 because 2 raised to power 2 is 4. Shemi? Yes. Then I now have L, right? So please, the formula for finding moment of inertia, notice they made a mistake in that your textbook. The formula for finding moment of inertia is actually T squared, that is from this, T squared mgd, T squared mgd. And this formula will help us. Notice that there is difference between finding standard error and finding error. Are you aware? No. I've said it before. There's a difference between finding standard error and error. I've said it before. We even have things like percentage error. I've said it before. Even the time we did, yes, even absolute error. I've talked about error so much in this class. Then when we talk about those sources of error that I told you, things like systematic error, random error, and your procedural or human error. I've touched error well in this class. So, but please, we've derived inertia. Let's go back to what we're doing, which is trying to get our slope of t divided by 1 over d. That is what we're trying to do here. And by the time we do it well, we should be having this to be td is equal to. So that is what I want us to do. I can clean this table. So you've written this. So you use it to try and plot graph when you get home. So please, once we do cantilever, we can start our alternative to practicals. Now, I have from this place, I have t squared mgd squared over k squared l is equals to k squared il. Help me now.
Over K squared L.
Hey, ụmụaka na-emere tutorial. Is this thing correct? Check.
Yes.
I'm not supposed. Tell me what I'm supposed to have. Like this, Shemi? Yes. Now see. Then I have k squared il, Shemi? Yes, that is where we are before trying to divide so that we can get I. So remember what we're trying to do is to get slope. Anytime you want to get your slope, I told you that how to check if your slope is correct is by doing the left-hand side that gives you what you've plotted on your graph should be equals to the equation of that particular question. So of that particular practical. Showing you that whatever you have from your slope is equals to, if you solve the equation, is equals to left-hand side equals to right-hand side. So that means by the time I've gotten this, I can say divide both sides by mg. Divide by mg. This we get out. So I now have t squared and d squared. Do you know that this is something I'm saying cd squared? Shebi, you know? Yes. Multiplication. This is what we call distributive power law. It can enter here, it can enter here. Now this is not equals to k squared il over mg. Shebi? I can say take the square roots of both sides. This will cancel this so that cd will be equals to roots k squared il all over mg. And do you remember that k squared is the same thing as saying 4 pi squared, Shebi? il all over mg. There are so many things. Sometimes you might see this thing as force, but so when you know this, as we progress, you will not start to see most of the things we are doing as practicals. We'll still treat it as a topic. So when we start doing the topic in Physics 101, you now see us throwing more light, showing you other things that this same thing can be. So that means, what this thing means is that by the time you do your practical, whatever you get as your slope here should be equals to, if you solve this thing, the answer you get from solving this thing should be equals to the slope you have, or close. If it's not close or the same, that means that your practical, you need to redo it. You understand it now? It's very as simple as that. You have question? Yes, that's what I'm saying. That's what I'm saying now, that I noticed that in this book, they did an element of inertia. The person that did this thing actually wanted to do something, but he went to do magic. So this 16 here is supposed to be 4, not 16. So note that. So please, that moment of inertia where you have 4 here. Here, 4 is 4, not 16. It's a mistake. If you check, there are so many mistakes they make. Even that one we did the other time. That one we did the equation there. They actually converted the O to have just the denominator, no numerator. So, if I've noted that, let's check the second question here. Please, remember I said, for that part of your slope, what you have to show them is that whatever you have your slope, if you come here, maybe you got 0.5. You come and do 0.5 is equals to everything here. So that if the person is checking it, come and put all the things you have on this and solve, the person should get the same thing you have. Ask. Yes, that's what it means. I ask.
Some of them is carrying that square. Can you like J4 I L square, MG square?
I don't know.
2.
Can you do what?
Like, no, like see this thing.
That thing is of no use now. Is it not secondary school? You don't do that kind of thing here. That is me coming to come and do, maybe I come and do 4 pi square. Who are you trying to prove to that you know? Maybe you come and do raised to the power 1 over 2 all over mg. Is it not what you're trying to do?
4 pi square will have its own square root. IL will have its own square root. Everything will have its own square root.
Okay, I thought you are reasonable, sir. No, it's not like how. I mean, with what she's asking now, is see, I don't know your plan. I don't know your plan, what you're trying to do. But what I'm saying is that imagine we come and do 4 pi square roots, IL roots over MG. You self check it now. See, my friend, this thing now, cancel 4, this thing here, is best left this way. You are not wrong though, but what I'm saying is that we don't have room for that. What we are doing is the slope. So we are not trying to get back anything we started with. The slope is equal to this value. We are not trying to, and notice that one you are doing, that one you are doing, sir. Have you noticed that this D here must compulsorily be close to this D? If it's not here, it's no longer the slope. So if I want to do that thing we did before, that means that this one, we have to leave here and come here. Please, provided you grant it, you are free to think however you want to think. But make sure that however you want to think, we are doing the same thing we are doing. If I sit down, wait, so do you think it's only you that think? If I sit down with pen, I discover things. Yes. But guess what? After discovering things, I'll still tell myself, you are still normal. Don't do this one. Stick to the normal thing. So, as long as you have this thing, you are in order. Think to any direction. But let's be doing the normal things for everybody here that is normal. And you know that the word of greatness belongs to people that are not normal. That's what they say. So let's hide ourselves and attend to people that are normal. Oh yeah, give me the second one. Please, you are free to think. That's what I'm saying. We've gotten it now. We've gotten it. So to calculate moment of inertia is simply as I have this now. See, I now have I equals to Z squared. M, I have G, and just substitute. You get the final answer. You understand it? See, if you don't understand, you say, see what they're saying. What they're saying here is at that point, you have to show them this equation. What that person is saying is that at that point, you have to show them this equation. Please, I'm not going to solve this moment of inertia now until we find the error. Let's find the error first. We'll then come back and now put the values here to solve. Is it confusing? See, I said, at that point when they say find the moment of inertia, the same way we try to derive the equation and we got that I is equal to this thing. Use that same equation, run down till you get I equal to this squared and 2b. square, all over 4 pi square L. When you get it, I am not saying that if we finish getting the error in slope, we'll not come back and solve this moment of inertia. So let's check the next question.
Calculate the moment of
So I will leave this part, I'm not doing this part. It's in tutorial class that impregnates you. Hope you know. Okay. I'm talking about academically. And when you go home this Christmas, for those of you saying, I want to go home, I'm tired. By the time you stay 2 weeks, you start missing us. You open your textbook like this, the energy is no longer there. You use chicken to finish everything, then you don't remember to do that. That is why the very first week we are starting tutorial, you will see me in your house thinking it's a joke. They will just come and post on WhatsApp today's tutorial. We'll shock. We will not post everything. We'll just post to let you see that we've started. So by the time you stay that week finish, the upper week, you must come back. I have said, to find the error, notice that from here, please, they did not say standard error, they said error. Know the difference. I've shown you 2 methods of finding standard error. Either when we are using standard deviation, or when we are using the product rule. That is just saying, whatever I have here, the changes. Multiplying. But when it has to do with error, we make use of what we call the actual or absolute error, or you call it the fractional error. Sometimes people say it's percentage error, but I don't say it is percentage error because percentage error has its own methods of calculating it. You have to include even the 100%. So what I'm teaching is the absolute actual value method, or you call it the fractional method. So I say that I will be equals to. Notice that right there, this 4 pi square was gotten by doing K shaping. Yes. It's a constant. I have no business with it when I'm doing error. So it's going to be simply T square mg T square over L. Now check. This is a quantity called time shaping. Yes. This is a quantity called mass. Shaping. This one is gravity, shaping. Yes. Gravity that I have here is also a constant. So I'm removing it. So this is a quantity called distance. And this is a quantity called length. And do you know, they are the same quantity, but notice that they mean different things in this practical. This one is simply distance of separation. This one is simply length of strength. Is it not true? Length of strength. So please note, you can say on your notebook notes, for any quantity, let's say this is Q, equals to A raised to power A. Then X raised to power, let's say B. And let's say Z raised to power C. For any quantity A, X, B, Z. To find the error, this is the formula you're using. Q will simply be, that is error means change in Q, will simply be equals to change in this A all over A. This is the power shaping. This is power and shaping. Multiplied by the power. Plus change in this X all over this X multiplied by the power. So let's say this one does not have power. That means this will be just plus change in Z all over Z. So using the same principle now that you know for when it has to do with error. Error means changing. I did not say standard error. I've shown you standard error. Oh, you're using the same principle now. Help me. Help me. Using the same principle now. I will be equals to
Changing.
Times 2, Sherry? Yes. Because this is the power. So when M won't come?
Change in M all over M.
Sherry?
Yes.
Plus 2. Sherry?
Yes.
Plus what?
Minus.
Think now. It's the same thing. See, whether down or up, when it has to do with error, this will simply be the same thing as saying just change in error all over N. If it is a standard error, I will consider that this thing is down. You catch it there? I just do, even if it's standard error, what I'm just doing is changing. Okay, catch it? Or I can use that my standard deviation, where we now finish, we now come and do this over root L, all those things. So please, but when it has to do with error, please, I know I've stressed on it. Even the one who did that changing, this changing here, if it's not given, we simply use that degree of accuracy. Do you still remember? Yeah. Divided by 2. Hope you still remember that day. Yeah. So I know we've spent a lot of time on error for us.
I did a video concerning it.
Yes. We made a video. It should be viscosity class. Is it your modulus class? Which one? Which class was that? Was it viscosity or your modulus class? Okay, just me. What I know is that I will have it in mind that I am posting 2 videos today. That is 1 that is with video of the practical. 2 that is with standard error. 2 videos. 1 on the practical, 2 standard error. This one now, the video is already here. So I will just, what I will do is I will break it down when I'm making the posting. I will cut it so that the part of the video will start to one side, so that we can now be able to watch it anytime somebody asks me for it. So please, with what we've done, I want to claim. He said, why is what? G is a constant. Everything that is a constant, I'm not including it. G is a constant. Acceleration due to gravity is a constant. I am not including it. That 2 pi is also a constant. I'm not including it. Notice that the only things I'm including are things that can give me error. For example, the rope, there is that string attached to that rope. As I'm flinging it, as I'm taking it at an angle, I might, as a human being I am, the adjustments I'm making, I'm not actually very 100% sure that I'm doing it the way it should go. So we make room for that. The same thing with the distances apart. The meter rule itself on that particular distance has what we call its own error. The same thing with when I have to do with what's it called, even the measurement of that my strength as well. The meter that I'm using to measure it has its own error. Then when I come to the inertia as well, the inertia I'm getting, this inertia that I'm getting, has its own error as well. So that is why I am making provision for the error using the things that can give me error. And remember that since we are talking about error here, this becomes change in I, hope you know. Inertia, that becomes change in I. So everything here is simply change in I. Error means changing in that physical quantity. So let's now use this thing that we have now to see if we can get error before we now come back to this. I am meter rule. Please, meter rule for the length. We have meter rule to be 0.1 normally, should be divided by 2 gives me around 0.5. But please, what we are going to be considering is the practical book. Check if they gave us any increment, decrement. I told you that is how you get your change. Did they give us anything like increment, decrement? No. They didn't give us anything. Wow, let me see. It's supposed to be close to the table of value. Just check other practicals. They normally put it now. Okay. Oh. So please, for the length of the string, I want you to use 0.001. I'm thinking of YX standards. Then the distance, (0.01). For mass of diameter rule, 0.01. Time normally is supposed to be 0.1, but I can maintain 0.1 actually. I maintain 0.1. Do you know why I use 0.001? Please, micrometer screw gauge. What's its degree of accuracy? 0. Okay. So I am trying to use that micrometer screw gauge reading for these two. Vernier caliper is 0.01, Shebi? 1 meter rule is just 0.1. So I'm taking it that I use micrometer screw gauge to gauge my rope and then the distance, and that's YX standard if I'm not mistaken. But if you can check for me, YX meter rule measurement or standard says we are not provided with time here. So what I'm trying to do is I'm trying to use values from WAS exams. So please check if it's 0.001 they're using. But for degree of accuracy behind, this two should be correct. Time naturally is 0.1. So please check if it's possible, check.
Check what they got.
Don't worry, let me help myself. Anyone? It's not here. So please check for me online. Check for me online if you can see any standard degree of accuracy for the mass of meter rule. Check for me degree of accuracy for the mass of meter rule. Check online if it will correspond to 0.01 or 0.001. We need to be sure. Please check for me online the degree of accuracy for mass of meter rule. I want to be sure if it's 0.1 or sorry, if it's 0.01 or 0.001. It's not here. Check for me online the degree of accuracy for mass. You know, it's something we do with what is it called? Vernier caliper or micrometer screw gauge. So minus. So see what I'm doing. You know what I'm taking? I'm taking it that if a vernier caliper can measure these things, if I need higher accuracy, I use micrometer screw gauge. Since micrometer and vernier caliper can measure it. So what I'm now saying is, what did you get? For mass,
0.1 centimeters.
0.1 for mass. 0.1. Are you sure? Let me see. No, this is not what I'm looking for. What you are doing, what you are actually checking, I said mass of meter rule. That thing here, what you check is like what you measure with meter rule. The degree of accuracy of anything you measure with meter rule is 0.1. Yes, like when you use micrometer screw gauge or So 0.0 plus or minus 0.01 or 0.1. So let's use 0.01. So see how we are actually doing this is not something straight. See what I'm doing. I'm saying since it's mass of meter rule, micrometer screw gauge can measure it. Vernier caliper can measure it. Which one is more accurate? Micrometer screw gauge is more accurate. So I'm using that degree of accuracy for micrometer screw gauge. This one, 0.01. So if I have this, please, now let's substitute. Let's try to substitute. Let's try to substitute. The time, the period. What did we get as our period? Let me see what you've written down. These values they did not give us is really affecting us because we have to think about everything. So what we are doing now is what practical could have done. So that is what we are doing now. Ready for you. Don't worry, once we finish this one, we go whatever. Phone number one, password. Once we finish this one, we go. Okay, see what they're telling me here. They said there's no single, listen, they said there's no single standard value for moment of inertia. They said there's no single standard value for moment of inertia because it depends entirely on the object's mass, shape, and how it's suspended. But they gave us cases. They gave us cases where we can have 0.0168. Okay, please. I want us to use our moment of inertia. I want us to use I to be 3.699. They said the research study shows from 3.69. And in the textbook I have, is the same thing there. So please, let's use that value. It's not given to us, but let's use it. Because for us to get this period, see what I'm saying? For us to get this period, because we need period here now. We need period here. For us to get the period, we need to know what inertia is. And they did not give us period. And I don't want us to come and do, we can actually sum up our period. Hope you know. We can actually sum up our period. The whole period we got. Equate it. But please, as we are summing that up at home, we now use it to check if it will correspond to something close to this. So please, sum up the period you have there. Let's check something. Sum up the whole period you have. Sum of all the period. That is each 1 minute. Yes, sum it up. What do you have? Everybody sum up. Let's see what you have for the whole period here. 6. Is it 6?
Yeah.
You got the period to be 6, Chevy?
Yeah.
Well, let's check something. Let's see if it corresponds, if it's close. Let's see. I come to that formula for period. I do C squared equals to 2 by root IL over MGD squared. Chevy? Now you do for me. So the T, Chevy, like this. T equals to 22 over 7 root. Moment of inertia. Let's put this in. Let's see. 3.69, Chevy. It can vary, but I just want us to check. The length of the string is what? 70. But we need to convert it to meter. 0.7, Chevy. Okay. All over our mass. They didn't give us mass, Chevy. No, now that question, check. If you check that particular question, we did this practical we didn't use mass for it. Check. We didn't use mass. Did we do mass? So you see, what it simply means, the issue, you said? We assume yes, they didn't give us mass. So what we are taking there is simply the mass of that meter room, which we got to be what? No, 80, Chevy. Is it 8 or 86? I said that time. 80. We convert 8 for me to see it. 0.08. Is it 0.78 or 0.8? So how come you got 0.7 here? Okay, this one is length. Okay, yes. Okay, yeah, this one is very important. Then the G is 9.8. Now, the distance from the distance from a particular place to another particular place, you know that we vary this distance. Do you still remember? We use different cases now. We used when the distance was 80, when it was 70, Chevy. We used it for different cases. So a situation whereby, let's say I sum up everything and divide by the mean, what do you have? Are you understanding what I'm doing here? We use, when we have 8, 70, 60, 40, Chevy. Let's say we add up everything. Chevy is 5, this thing we did. Divide by 5, let me see what we have. What do you have? Everybody should do it too. What do you have? 60. Well, if you convert, that's in cm, Chevy. If you convert it to meter, what do you have? 0. What? 0.6. 0.6. Oh yeah. And this is square now, Chevy. One punch for me. 0 point again. Punch everything. Let me see what you have. So please, wait up. The length we use here, that is for the rope. We have it, Shebi, it was given. Okay, punch for me. Accuracy is very important, that's why I'm checking it again. Here for me. Do 2 times 2 over 7. Then whatever you have, keep the answer. Then do roots. 3.6 times 0.1 different. What do you have? 19? 19. So your T is equals to 19 in seconds. 19 in seconds. So you see, what actually affected our value is this, Shebi? So what I will do, if I don't believe in this 19 seconds, it will simply be, if I use that my 6, you got total of everything summed up to be 6. If I go and put that 6 here, whatever value it gives me will give me the inertia that I have here. Then I can carry it back and put it, let's see what I have. Let's try it. Is it confusing? Yes. So please remember we assumed this one. And you know why we assumed? We said we looked up. Then I gave us that for most cases, moment of inertia is 3.69. They have the part where they gave 1.089. They have different cases. So case 3, I chose this one because it reflected with what is on my own textbook. So we are saying a situation where we don't assume this moment of inertia and we use the time we got, which is that 6. And we come and make this now solid of formula. We solve with this. Let's see what it will give us our own moment of inertia. Are you getting the point, class? Which one? I said, this 19, we got it because we assume this. That general standard. The distance was gotten by summing up and then taking the average. Sum up all the distances you have. Take the average. Is this 75? It should be 60 now. 60, Shebi? Wait. What did you put here? In your own, what did you put here? No. Don't put 19, put 6 here. Let's see what you have. Put 6 here, let's see what you have. So please, let's solve that moment of inertia together. My problem with the question is that we have to assume a lot because they did not give us readings. So I have I equals to. So let's put that 6 you got. Shebi, you got 6 square now. Then MO, what is the mass of my meter rule? 0.6, Shebi? Mass of meter rule, 0.08. Then I have G to be. Then the distance. 0.6. All square, Shebi? All over. 4 times 22 over 7. All square. Then the length. 0.8. So it's 0.7. 0.7. Okay, 0.7. Oh yeah. Watch for me. What do you have? 0.368, right? So 0.368 in meter now. In meter, right? Is it meter? Yeah. Somebody please check for me. If this thing I got, Shebi, this one was in kilogram per meter cube. There's something fishy to this. This is in meter. Shebi, you know it's 6 we got, Shebi?
Where did we get the 6?
The 6, now the 6 is from our time when you sum up the whole period. Sum your period. Convert this thing now. And notice, so inertia is actually in kilogram per meter cube, Shebi? Is it? We're having 0.36. That one is 3 points. And this is approximately 0.37. We are not wrong, but I'm checking if there's any way we can beat that. There are different cases. Are you okay? So please see what you're doing for me. What we got, please, what we got, carry it. So we're not using 3.6 now. We are using. Is it confusing?
Yes.
It's not supposed to confuse you now. That 3.69, I picked it online. Out of the 3 cases they gave us, they said a research showed inertia to be 0.06 whatever. Another research showed, and they said inertia is dependent on mass and whatever. We are the one that use what we use. So our practical should reflect our time. So please, our time, the total period is 6. So we use that total period to solve, and we got this. And if you check, if you really check, you will see that there is close proximity. Because if what we have here times by 100, thereabouts, we should be having there about 360, or is it 36 point whatever, should we? So there's close proximity. So I'm saying let's use what we got from our own practical. Substitute it there. 6.02 seconds, should we? This is our period. So we are using what we use for our own practical. Online did not do the practical with us. Ask. No, naturally it should be kilogram meter square now. From that time we did MR square, so you should know. This one is kilogram now. Meter square. You should know. This one is density now. I'm thinking plenty things. I'm doing this, I'm thinking about where this one is coming from. So all these your AI things. Give it to one side. Give it to one side. So please, this is our inertia. This is our inertia, and this is our time. So, any other question there? Please, we should be correct. The confusion is coming from the fact. The confusion is coming from the fact that we went to go and use online. But notice that our period, we are the ones that assumed what we assumed when we started our time. So the mistake is that we went online to go and look for a value which is wrong. So please, what is the error here? The error in our value, now notice, we now have t to be 6 seconds, shall we? So to get our error is simply, I want to clean. Remember, we already did changing I to be coming from, I got c square here, shall we? You see what I have?
Yes.
N all over mgd square, please, is it correct? That time I made the next subset of the formula. Check.
No.
Oh, yeah, give me now, participate. Mg. Over L. Okay, so from this place I now need that changing I will be changing t squared. So check 2. Shall we? This thing we are doing, when I start teaching you second semester chemistry, you still see us applying something like this. So plus shall we? So let's now impute the values. If you like, you can say we are wrong. Moment of inertia is dependent on your mass, your shape, what you did. So we don't go and pick other people's practical and come and put for our own. So we have to use our period. Why I picked that is I wanted us to check. And if you really check, if you have spiritual eye, you will see that what we have also falls in that range. If you have spiritual eyes. But if you don't have, wait till the lecturer gives you value. We now use the value and so. And once we do cantilever, from our next class, we now start doing those practicals that involve values given to you. Those are alternative to practicals. And please, notice that today's class, people in this class are not even up to half of our students. You can look back and check. Why I'm saying it is that if by Monday, students decide to come to school, the way they should, we might change our mind and stay back till 20. It's just the way we observe. Saturday class is always bigger than this. So good number of persons that must have gone home. Alright, so to get that arrow will simply be on your watch. Changing I will be equals to. You did biology today. You did parasology today, Shabi? Please, all these things they normally teach you, they'll be calling us questions. They will say, and all these things. I hope it's not just you reciting. You still go home on your own to read those past questions. We're not saying it's a must to buy past question. No. Shabi, this girl wanted to photocopy snap past question. I allowed her. You can snap, provided you are reading it. So be combining what we are teaching you with the fact, Nubia, sit down. We are about to go home. How can you be going on without prayers? We are about to go home. Let's just finish this one. I am the first. Changing T now. What do we get as our changing T? Number. Changing T is 0.1 and that increment. All over the T is 6, Shabi?
2 times.
Everything times 2, Shabi?
Yes.
Plus mass. What do they give us as mass? 0.8. 0.08. Then the change in mass is what? 0.1. Okay. Plus 2. Notice that if the standard error I'm looking for, I will go and divide all these things by 2. Do you still remember? But I'm just carrying those increments and putting it in. Oh yeah, for D, I have 2 times. Changing displacement is what? I'm using this thing because even 0.01 can work it. But I'm just using 0.00. Please, the degree of accuracy for me, micrometer screw gauge is 0.what? 0.001, Shiri? So I'm taking it that I need accuracy. I'm using micrometer screw gauge. So all over. That D is what? The distance given distance. That is after we checked, it was 60 now, Shiri? That's the average. 0.6 plus the length. The length is around 0.7, Shiri?
Yes.
Then change the length.
0.001.
How I wish you are following this thing. How I wish you are following me. Oh yeah. Now please, I know you are following. Now please, punch these things. Let's see what you have. Change in I. You will think we are joking because we are saying we are getting this, we are suffering to get the values. But do you know one thing I've come to understand about practicals? Once we finish this thing, even when you are giving value, you see that because we follow all the rules and standards, it will tally. It will tally. So as we are doing this thing, we're writing it down. When you finally do the practical, observe. You see, do for me 0.1 divided by 6 times by 2. You
0.033.
0.033. Okay. 1 plus Shabi is like this. 0.01 divided by 0.08. 0.125. Plus 0.001 divided by 0.6 times 2. 0.0. Okay. If you like, go to village and enjoy yourself where you are running from masquerade. The way you carry yourself there, you should come back better. Don't come back here. You are carrying one bandage, God forbid. So return back better. Is this thing correct? Check.
Yes.
Plus, do for me 0.001 divided by 0.
0.001.
Like this.
Put 0.
Okay.
0, 1.
Another 0.
No, 1.
Okay. Ngwa. Add up everything for me. 0.163. Like this.
163.
Which is approximately. Even is approximately 0.2. Are you aware?
Yes.
So I want to use 0.2. So change in I is actually 0.2. And notice that means in kilogram, Shebi, you know, meter. Hope you remember that formula, mr squared. That is kilogram r. So if I like, I will not put it. When it has to do with change, nobody will disturb you to put the units. Because it's changing, nobody will disturb you. But when they will disturb you now is to come back. That your I, that your inertia. Your inertia, what did you get? Tell me what you got for inertia.
0.37.
0.37, Shebi? It should not be plus or minus 0.2. This is your inertia. Your inertia now should be 0.37. Increments, decrements. Anytime you see any value given to you and you have this plus or minus something, it simply means changing is this thing. That is why I'm asking you for all these things from that thing, because normally a standard practical will just come and give you on top of it. It will just write plus or minus, all those changing. But because they did not give us, we have to start everything from the beginning. Child of God, believe you me, that if you go and study all the practicals we've given you this semester, as you go on for Christmas break, study all the practicals we've done and come prepared. By February, once you write your exam, you'll be the one entering DM to say, Sir, God will bless you. Because if you don't tell me God will bless you, second semester, I will just be teaching you only physics. I will not be doing the practical. Yes. So please, take your time and study this during the holiday. Somebody should pray for us.